I looked during the video introducing the idea of rotational kinetic energy. I looked a bit at an example of rolling down a hill, but I want to do this one with some numbers too. So this is rotational kinetic energy. That is kind of my topic, and I'm going to do an example of rolling downhill, just to see what a problem like that might actually look like. So I'm going to have a hill like this. We're going to give this thing an initial height, or we're going to give the hill a height of, let's go 10 meters. It's a big hill. I'm going to put an object at the top. It's a side view, so I can just draw it as a circle. We can make this thing a solid cylinder, because why not? A solid cylinder will have a gamma of 1/2. We can give this a mass of 2 kilograms, and maybe a radius. We ultimately know the radius isn't going to matter, but let's give it a radius of 10 centimeters. We're going to start it from rest, and I would like to know the speed at the bottom. Questions that I cannot ask are, how long does it take to get to the bottom? Because my acceleration is changing the whole way. What I do need, though, as far as information goes, I do need to know there is sufficient friction to roll without slipping. Sufficient friction to roll without slipping. Here we go. I'm going to say, here's my initial energy, here's my final energy. I will have potential, kinetic, and now that I am able to roll, I'm going to add in a line for rotational kinetic energy. I need a place to call height equals 0, and I like the ground down here for that. You can put it up here, but if you do, then your final height's going to be negative. Not a problem. I'm just not choosing to do that. My initial potential energy is mgh. I know all of those values. My initial kinetic energy, I'm starting from rest. My final kinetic, or my initial rotational kinetic energy, I'm not rolling yet. My final potential energy is 0. My final kinetic energy, I'm going to have 1/2 m v final squared, because I am making it to the bottom, I'm moving forward. And rotation, 1/2 I omega final squared. A big thing that I need, and I do have, is right here. As soon as I know that I am rolling without slipping, I'm going to say V equals R omega. So this thing, I'm going to write as 1/2 I times V final over R squared right away, because I'm rolling without slipping. So let's keep going. My initial energy was just mgh. My final energy, I've got 1/2 m v final squared, and I've got 1/2 moment of inertia. Moment of inertia is gamma mr squared times v final squared over r squared. I'm going to cancel my r squareds, and then I've got m in every term, so I'll cancel that too. Left side remains as g times h. The right side is, I've got 1/2 of a v final squared and I've got a half of a gamma V final squared, meaning I have a half of a V final squared times a 1 plus gamma equals GH. Still moving. I'm solving for V final. V final equals 2GH over 1 plus gamma, all under a square root. I can plug in some values. 2 times G times H is 10 meters over 1 plus gamma. It's a solid cylinder, so a half. And I can plug those numbers in, and I get 11.5 meters per second. What if I have a part B to this question that says, let's do it again for a hollow cylinder. A hollow cylinder or a hoop. Well, I can use the same exact equation. I just need gamma to now be 1. When I do that, I'm replacing this 1/2 with a 1, and now I get 2 times 10 times 10, that's 200, over 2 is 100, the square root of that is 10, so now I'm going to get 10 meters per second. The problem's not any different. I don't have to refigure anything out. I just have to plug in a different gamma. If I wanted to say, what does this look like if I have a block that's just going to slide down and there's no friction at all? Well, then I'm going to plug in gamma equals 0, and I'm going to get the square root of 200 over 1 plus 0. The square root of 200 is going to be 14. So then I'll get 14.1 meters per second. It'll be going a little bit faster because none of the energy that I have, how do I say that? MGH, this left side, the initial side, is kind of my energy budget. Is how I think of it. That's my energy budget. And then my final side, that's what I'm spending it on. So I have a total energy budget to start with. And in the case of the solid cylinder, I'm going to spend some of it on moving forward and some of it on rotating. Because my gamma is small, I don't have to spend a whole lot of money on rotation. So more of my money can go into, more of my budget can go into forward motion, and I move faster. With the block sliding down a frictionless ramp, I don't have to rotate at all, and all my energy can go into forward motion. So it's going to go faster. With the hoop, the hoop requires a bigger price for rotating. More of my budget has to go into rotation, which leaves less left over for forward motion. So that one moves slower. I don't know if it's a helpful thing for you to think of it in terms of an energy budget, but to me that makes a whole lot of sense. That's an example of rolling down a hill.